So far we learned about line integrals. If you have a scalar function, line integrals along a smooth curve C. So we said that, hey, if we have the integral of f of x and y or x and y and z along C, then this guy is just converted into f of xt, yt, and the length of your curve, which is dx dt squared plus dy dt squared dt, and suppose t ranges between a to b. So this is for a scalar function, f of x, y, and z. Now we are interested in knowing, well, what if we have a vector function? So this is for scalar function f. Now line integral along curve C for a vector function. Well, in this case, if vector function f, so I'm going to use bolded letter, is continuous vector field, it means that all of the components for your vector function are all continuous functions defined on a smooth curve C, given by the following vector: r of t is equal to just the vector function representation for C, and your t is bounded between a and b. So you have a continuous vector function over a smooth curve, which is also given by rt, which is a vector function. Then the line integral of f dot dr, so bolded letter f, and also your r as a vector. Guys, here you're dealing with two vectors. That's why we need to have an operation between two vectors. Can be written as the integral of f of rt dot the derivative of your vector representation for your curve C dt, or just the integral of f dot t ds over curve C. And t ranges between a to b. Just a recall for those of you who need to refresh your memory. Vector t was defined as r prime divided by its length. Very good. Let's go over one example to feel more comfortable about what's going on here. Example. Question says, find the work done by the force field, which is a vector field f of x and y, which is given to us as x squared I minus xy j in moving a particle along, well, the path given to us is quarter circle the quarter circle RT is cosine t, sine t, and then t, of course, is bounded between 0 and pi over 2. Very good. So between these two formulas, since this function is a vector function, you're going to follow the second formula. The first formula applies when you have a scalar function. The second formula applies when you have a vector function. So take a look. Since we have a vector function, the line integral f dot dr along C. Well, here I have my x, I have my y, and I'm going to do the substitution here and then multiply that by the derivative of the vector, the dot product. It's going to be the integral. Well, here I have my t bounded between 0 to pi over 2. And if I plug in this guy here, I have cosine squared of t, comma, negative cosine t, sine t. This is my f of RT, dot R prime of t. R prime is going to be negative sine t and cosine t dt. Very good. This guy becomes integral 0 to pi over 2. So the dot product, you multiply the first component, you multiply the second components and add them together. It becomes negative sine t cosine squared of t minus sine t cosine squared of t dt, or the integral 0 to pi over 2 negative 2 sine t cosine squared of t dt. You can use u sub, u equals to cosine t and du negative sine t dt. Perfect. So this integral becomes 2 1/3 cosine cube t 0 to pi over 2. And let's see what do we have here. That becomes negative 2/3.